Hello, in this video I'll be discussing the sampling distribution of the sample mean. And so I want to start out with a little motivation for this topic. And so let's review a random variable that I'm going to call x that has a value that's determined by the roll of a die. So I can construct a probability distribution for this random variable. It can take on the values 1 through 6. And the probability that this random variable will take on any one of these values is 1/6. This is a discrete random variable, and in particular it's a uniform discrete random variable. And this is the probability distribution for that random variable. All right, so if we were to look at some observations of this random variable, where we tossed a die, maybe initially the random variable takes on a value of 3, and then the next observation is a 6, and 4, and 3, and so forth. So in this table, I have represented 50 values for this random variable. This is a 5 by 10 table. And so now this distribution that I'm describing here is called a population distribution. And so these are in the very long run, these probabilities should match up with the proportions, and we say that the proportion, the probability is defined by that long run proportion for the population. All right, so in the next, the section that's coming up, we're actually talking about something a little bit different, and it's called a sampling distribution. So a sampling distribution distribution of a statistic. Now remember, a statistic is a summary from a sample. Examples would be like the sample mean, a sample proportion, etc. I'll just put ellipses there. A sampling distribution of a statistic is a probability distribution. I want to just abbreviate some things here. Distribution for all possible values of a statistic computed from a sample of, I'm going to go on my page here, from a sample of size n. So I'm going to go back to my initial table here and see if this helps us distinguish between the population distribution, which is what we have pictured in this table, and what we mean by a sampling distribution. So I'm going to focus on the sampling distribution of the sample mean, which would be x bar. And so let's look down each of these columns and consider this to be 10 samples, each with, let's see, there are 5 rows here. So this would be, we'll say n equals 5. And so I want to calculate the mean for each of these samples. All right, so I've actually done a little bit of this work ahead of time. For the first sample, the mean, this is going to be x bar, was 3.6. For the next sample, it was 4. This is 2.6, 2.4, 2.8, 4.2, 3.2, 4.4, 4, and 4. So if you add up the observations in these 5 observations and then divide by 5, you should get 3.6. So each one of these is a sample mean. We could call this one the first sample mean, the second sample mean, the third, and so forth. And then this would be our 10th sample mean. Now, in this section, I'm actually interested in the distribution of these values. Now, if I did this many, many times, one thing that I might do is construct a relative frequency table and then maybe look at a histogram. So of interest to me in regards to this distribution, I would certainly like to know where the center of the distribution is. So I'd like to know something about the center, something about the spread. So by center, I mean, what's typical? What's the typical value among these sample means? Usually we do that by looking at the mean. And now, knowing that these are going to be spread out, and I want to know how spread out are these sample means, and so I'd like to know the standard deviation. And finally, I'd like to know, if I can, the shape of the distribution. So these are the 3 things that I'm going to be investigating. So again, I'm looking for what's the mean among all these values, what's the standard deviation among these values, and can I determine the shape of the distribution of these sample means. All right, so something that's handy to know as far as for our center, in other words, the mean, and for the spread, in other words, the standard deviation. We can look at how those compare for the population distribution and a sampling distribution. Okay, so let's go back to this table here. So when I'm looking at the values here in the middle of this table, these are different values from our random variable x. They've been determined by the roll of a die. Here is the population distribution represented in a table. You may recall that the mean for this distribution, because it is symmetric, is right in the middle of these values. It's actually 3.5. So I actually took the mean just in the sample and of 50, and I got pretty close. It was 3.52 for those 50 values. But if I could do this many, many more times, the long run mean in the population distribution is 3.5. Now, we represent that by the population distribution in the center. We use the symbol mu. That's the long-term average value for our random variable x. In the sampling distribution, we'll use the symbol mu with a subscript of x bar. So this is the mean among the sample means. In other words, it's the long-run average among these values. So it may or may not surprise you to know that those 2 things are going to be equal. So when you average these averages, you get your population average. So this, the mean among the sample means, equals your population mean. So I would expect, in this example, when I take the mean of these x bars, to get 3.5. Just as I would if I had many iterations of this, the experiment where I'm rolling a die and was keeping track of the outcome. I would expect the long-run average of the individual values to be 3.5. So will the long-run average of these sample means. So that answers our first question about where is the center of the sampling distribution as far as when the statistic is the sample mean. Now, what about the spread? So in the population distribution, we use the symbol sigma to denote the standard deviation in the population, and the sampling in the sampling distribution, we'll use sigma, but with a little x bar in like the subscript position. So these aren't going to be equal, and I hope that makes sense. Now, when we look at the spread in the population here, we see values of 1, 6, 4. They range in values, and there's they differ from the mean by I think it's like 1.7. I'm sorry, that's the population mean standard deviation. But now, if we look at the variety that we're seeing here, just among the sample means, there's a lot less variety. So, for instance, I'm not seeing any 6s. In order to have a sample mean of 6, I would have to have a row of all 6s, which is a pretty unlikely scenario. If these are truly random and I have a fair die. I'm seeing values here that are much closer to the center of 3.5. So there's a little bit of variety. I do see a 2.4, and there's a 4.2, but generally speaking, I have values in the 3s and 4s. So the relationship between the population standard deviation and the sampling distribution standard deviation is this. The standard deviation in the sampling distribution of the sample mean is equal to sigma over the square root of n. So n is your sample size. Now, because n is in the denominator, even though it's underneath the square root, if you think about it, when this value gets larger and larger and larger, this denominator gets larger and larger and larger. And so this quotient then actually in turn gets smaller and smaller and smaller. So just notice that as n increases, your standard deviation in the sampling distribution of the sample mean will get smaller. It's a little tedious to say the standard deviation in the sampling distribution of the sample mean, and so this value we call the standard error of the mean. All right. So if I know that the, again, like for instance in the roll of a die, that this is 3.5, then I know that this is going to be 3.5. And if this is 1.7, if I'm taking samples of size 5, then this would be 1.7 over the square root of 5. Okay. So that's how we can find the mean and standard deviation in a sampling distribution. In the sampling distribution of the sample mean in particular. By the way, just to go back here, if we're talking about the sampling distribution of, if I wanted to be specific and say of the sample mean x bar, that's a probability distribution of all possible values of the sample mean computed for a sample of size n. In another video, we'll look at the sampling distribution of the sample proportion, that's p hat. Okay. All right, so that gives us the center and spread for our sampling distribution of the sample mean. In the next video, I'll talk about the shape of this distribution. I hope you'll join me.